Hey guys, this is Professor Janacek, and I want to tell you about vector fields. So we'll let f1 and f2 be functions defined in R2. Of course, we could have, say, f1, f2, and f3 defined in 3 space as well. A vector field is a function which we'll denote as here we go, as the uppercase F with the vector notation above it. This function assigns each point xy in our region to a vector. Notice we're taking a point xy and assigning it to the vector. The first component of the vector is defined by our first function. The second component is defined by our second function. Of course, we could also have the vector field in 3 space, which is f1, f2, f3. Again, notice it takes the points xy or xyz, and the first component comes from the first function, the second component comes from the second function, the third component comes from the third function. That's vector notation. Well, something like that. If our functions are continuous or differentiable, then the vector field is also continuous or differentiable. And the vector field is actually a vector valued function in several variables. So it's a combination of those two ideas of vector valued functions and now with several variables. Let's take a look at an example. I'll first look at the example where our vector field is defined by 5, 2y. So what we're going to do in this case, I've already actually graphed it because these can be very time consuming to graph. But the idea is that we're going to take a point. Let's say the point 1, 2. According to our function, the first component is 5 and the second component is 2 times y. Actually, let me back up. Let's do 1, 1. There we go. The first component is 5. The second component is 2 times the y value. In this case, the y value is 1. So we have 5, 2 as the vector. Now, what we're going to do is we're going to go to the point 1, 1 and draw the vector 5, 2. So at the point 1, 1, we have the vector 5, 2. And actually this doesn't quite have it, but it would be somewhere right in there. And again, you can imagine at the point 1, 1, we have a little xy axis. And then from that point, we're going to draw the vector 5, 2. Now these are typically rather small, just to give you an idea of where it is and what direction it's going and how long it will be. But if we had, say, the point 1, 2, that tells us that the first component is still 5 from our vector field. The second component is 2 times the y value. So we get 5, 4 as the vector. So again, at the point 1, 2, we're going to have the vector 5, 4. So again, at this point 1, 2, we're going to draw that vector 5, 4. And so we could also, say, take a look at something like 2, negative 1. Would give us the vector 5, negative 2. So at the point 2, negative 1, we would have the vector 5, negative 2. That one I actually drew a little longer than it should have been. It should be a wee bit shorter than that. But hopefully you're getting the idea. It's a little better. So again, you've got the point and the vector that I'm going to draw at that point. And of course we do this several times and we get our vector field. Let's take a look at this other vector field. F is equal to negative y, negative x, negative y. Again, just a few points. Just the idea, if I have the point, let's take the point 2, negative 3. Let me turn that around. Let's do 3, negative 2. Well, according to our definition for this vector field, we're going to just simply take the vector whose components are the opposite. So it's going to be negative 3, positive 2. So again, at the point 3, not sure what's going on there. Okay, at the point 3, negative 2, we have now the vector negative 3, 2. Looks kind of like that. So that's the idea. Hopefully you've got the idea. Again, these days we often generate these with some sort of vector field generator just to make life easier. All right, moving on. Let's take a look at a couple more topics of gradient field. We'll start with phi being a differentiable function. Notice I am using the Greek letter phi here. It's differentiable on a region in R2 space. Again, this could also be in R3. And then the way we define this, we have the vector field F, which notice I've got this notation which looks like an upside down delta, and then my function phi. And this is how we define it. So our notation is that upside down delta, which we called gradient, followed by the function. But this is how we define it. Notice we take the first partial derivative with respect to x, and then the first partial derivative with respect to y. So the first partial derivative with respect to x is the first component of our vector. The first partial derivative with respect to y is the second partial with respect is our second component. Notice, of course, if we were in R3 space, then we would have the first partial with respect to x, the first partial with respect to y, and the first partial with respect to z as our three components. In that order. Notice the first partial with respect to x is the first component. It's never the second or third component. This is called a gradient field. And our function phi is called a potential function for f. So let's take a look at an example here. We have phi is square root of xy. So if we want the gradient of phi, we're simply going to take the first partial with respect to x and then the first partial with respect to y and write that as the components of our vector. Well, looking at the square root of xy, looking at that function there, first derivative with respect to x gives us, that's going to be what? Chain rule, power rule, we get y over 2 square root of xy. And then the first partial with respect to y, it's going to be our second component. Again, chain rule, power rule, we end up with x over 2 square root of xy. And there we go. That would be our gradient field. Finally, that we have the idea of a radial vector field. So in this case, we're starting with this vector r, which is defined by x, y. We also have a function defined by x and y. So it's a function in R2 space, a function defined by x and y. If we take that function and multiply it by our vector, that is referred to as a radial vector field. All right, well, there you go. Enjoy.